everybody. Let's take a few moments to talk about forces and momentum and how they relate, specifically in the context of the momentum conservation model. As we move into this unit, you'll hopefully start to see why we took some time to talk about vectors. Momentums and forces have to be represented by vectors. Why? Because just saying how much momentum an object has or how strong a force is isn't enough. For example, providing a force upwards on this pen is not the same thing as providing a force to the left. When thinking about forces then, we always need to consider the direction that the force is in. Because forces can be represented as vectors, we can use all the same rules we know from vector addition and subtraction with forces. We can always add forces together just as we would with any other vector. Also, we can break forces up into their components. For example, one piece of the force that points in the x direction and one piece that points in the y direction. So why is balancing forces so interesting? This equation here is known as Newton's second law because it appears in Isaac Newton's foundational text about physics. What it says is actually fairly straightforward. It says that if you take all the forces on an object and add them up, the result that you get must be equal to the mass of the object times the acceleration of the object. For completeness, let's remember that acceleration and force are both vectors, so we'll include a little vector hat. Now, what does this equation say if all the forces on an object add up to 0? Well, it just says that the mass times the acceleration is equal to 0. We'll always be talking about objects that actually have mass. So if mass times acceleration is equal to 0, that means that the acceleration must be 0. Note that this does not mean that the object will not move. It just means that it will not accelerate. If, for example, you have an object at rest, and you push on it in a bunch of different directions in such a way that adds up to 0 total force, the object will stay in place, stationary. However, if you have an object that's moving, and all the forces acting on the object cancel out, the object will just continue to move at that speed in that direction until such time as the forces are no longer balanced. Consider an example that we just did, the 3 spring scales being pulled in 3 different directions. Let's imagine that this point here is the location where all 3 spring scales connect. We have 3 forces at play, one pointing down this way, one pointing up and to the right, and one pointing up and to the left. So what does it mean to say that the forces are balanced in this case? Imagine writing down these vectors in component form. Saying that these forces are balanced just means that if we were to take these 3 vectors in component form and then add them all up, the resultant vector would just be 0. It would have no magnitude and no direction. We're going to get lots of chances to explore how this works mathematically, so we won't do specific examples here. Instead, I now want to talk about a second idea that is related to the balancing of forces. It's conservation of momentum. Momentum is just defined like this. P is just the letter that we use to represent momentum. M is the mass of the object, and V is the velocity of the object. As with forces, it's important to remember that V is a vector. The object has a speed and is traveling in a particular direction. There are a couple of equations that we think about when we're talking about momentum conservation. I'm going to write them down, and then we'll talk about what they mean. This maybe looks like a lot, but there's not actually too much going on here. So let's take a moment to go over this. J is known as impulse. It's defined as the average force on an object multiplied by time. So for example, if I was pushing on this object to the right with 1 Newton of force for 1 second, the impulse that I provide to the object would just be 1 Newton second. So why do we care about impulse? Well, we care about impulse because it tells us the change in momentum. If you're able to calculate the impulse, you immediately know the change in momentum of the object. The 2 numbers are equal. But for For today, we're mostly interested about a very particular case. What does this equation say about what happens when impulse is 0? Well, if J is 0, then delta P must be 0 as well. In cases like these, we say that momentum is conserved. The momentum overall is not changing so long as all the forces are balanced and the impulse is 0. However, one key thing to note about this is we can apply these facts to more than one object at a time. So long as the objects are only interacting with each other, this equation will apply. For example, we can use this equation to think about the cart moving across the track. But we can also use this in the context of two carts traveling towards each other on the track. Because all the forces are between the two cars, the net impulse on the system is 0. The momentum of the individual cars is not conserved, but the momentum of the two cars together will be conserved. We have a nice little model that allows us to analyze systems like this graphically. Let's imagine the case that I mentioned a moment ago. Two carts are on the same track, traveling towards each other at the same speed. Let's also assume that their masses are the same. Let's draw a momentum chart to help us analyze this system. Our goal here is to fill in this chart with details about the momentums of the individual carts, the momentum of the system overall, and the changes in these momentum. Let's start by filling in the initial momentum of the carts. The way we set up the problem is that both carts have the same mass and are traveling at the same speed. Because momentum is just mass times velocity, this means that the magnitude of their momentums are going to be the same. However, because they're traveling in opposite directions, the direction of their momentums is different. Since cart 1 is moving to the right, it has a momentum vector that looks like this. Because cart 2 has the same amount of momentum, but is traveling in the opposite direction, its momentum vector looks exactly like the momentum vector of cart 1, just pointing in the opposite direction. So what is the total momentum of the system? Well, to find that, we just add up the momentum of cart 1 and cart 2. The momentums are equal, but pointing in opposite directions. So the vectors just cancel out, and our total momentum is just 0. We've set this system up so that there are no external forces acting on the system. This means that the change in momentum for the total system must be 0. So if the total system starts with 0 momentum and its change is 0 momentum, its final momentum must be 0 as well. But what about the final momentum of the individual carts? The answer to this depends on the details of the collision. In some cases, when two objects collide, they will end up sticking together. In other cases, when two objects collide, they'll bounce off. Which kind of collision happens depends on the specific scenario. Let's just pretend that these objects stick together. Well, what does it mean to say that the objects are stuck together? It means that they must be traveling at the same speed in the same direction. If this is the case, what is the only value that their momentum could possibly have? The answer is 0. When the carts were not stuck together, the total momentum of the system was 0 because they were traveling in opposite directions. However, now they are stuck together, so if they are traveling, they have to be traveling in the same direction. It's impossible for two objects that are traveling in the same direction to have a total momentum of 0. So the only possibility, if the carts are stuck together, is that they're at rest. They just run into each other and stop moving. Lastly, we need to fill in this delta P term for the individual carts. To do this, we just need to figure out what we need to add to this vector to get a final momentum of 0. In order for two vectors to cancel out, they just have to be equal and opposite. So the change in momentum for cart 1 is just the opposite of its initial momentum, and the same for cart 2. This is a complete momentum chart for this example. We'll see some more mathematical examples in the future, but we'll save that for later. Lastly, I want to look at one more case. It turns out we don't have to restrict these momentum charts to one dimension. We can also do them in 2 dimensions. The only difference is that now our momentum arrows are not going to point to the left or the right. Instead, they're going to be pointing in a bunch of different directions. Let's imagine the same exact case. However, instead of imagining the carts as being on a track traveling to the left or to the right, let's imagine that they're flying through space towards each other instead. I'll draw it like this. Now, first thing to note is that in this problem, it is true to say that the carts are not traveling only horizontally or only vertically. However, this is technically still a one-dimensional problem. The carts are traveling in only one direction. It's not left or right or up and down, but we can still imagine that this is one of our directions, in which case it's just a 1D momentum example. However, let's say that the only directions we're allowed to use are an x direction, which points right and left, and a y direction that points up and down. Let's draw a momentum chart for this case. We'll call this cart 1 and this cart 2. Let's do this same example, but now let's imagine that cart 1 is moving more quickly than cart 2. What's the arrow that represents the momentum of cart 1? Well, it's just pointing up and to the right, like this. What about the initial momentum of cart 2? Well, cart 2 is traveling in the exact opposite direction of cart 1. It's the same mass, but it's not traveling at the same speed. So its momentum is actually less than the momentum of cart 1. So the arrow for cart 2 just looks like this. Notice I've drawn this arrow to be shorter than the arrow for cart 1 to indicate that the magnitude of cart 2's momentum is less than the magnitude of cart 1. Let's try to fill in the rest of these. To find the total momentum, we just add this arrow to this arrow. To me, it looks like this. Unlike in the first case, the momentums are not canceling out entirely. What is the change in momentum for the entire system? Well, we know that it has to be 0. There are no forces, no source of impulse that is external to the two carts themselves. So momentum is conserved in this problem, and the change in momentum is 0. We therefore immediately know what the final momentum is. It's just equal to the initial momentum. Let's assume that the carts again stick together after they collide. As before, this means the carts must be traveling in the same direction at the same speed after the collision. Well, we already know what the total momentum after the collision is. So if these carts have the same mass, how much momentum does each cart have at the end? The answer is they have the same amount of momentum, exactly half of the momentum that the total system has. What is the change in momentum for the two carts? Let's start with cart 2. Cart 2 is initially traveling down and to the left, and at the end, it's traveling up and to the right. So what is its change in momentum? I'll draw it first. If we take this vector, the initial momentum, and add this vector, we get the final momentum. This vector has to be this long because it has to start by canceling out this vector entirely, and then adding on a little extra to get the final momentum to be in this direction. What about cart 1? Well, once we have the change in momentum for one of the carts, the change in momentum for the other cart becomes extremely simple. We know that the change in momentum for the system overall must be 0. This means that the change in momentum for the individual carts must be equal and opposite. This vector cancels out most of the initial momentum, but not all of it, so we're left with this little piece. While this case may be nice, there will be cases where the momentums don't line up in exactly opposite directions. If this is the case, you have to use all of your knowledge about how vectors add and subtract in order to find the final momentum. However, if you know how vectors add and subtract, this is extremely straightforward. You don't have to do anything special just because we're talking about momentum. What if you have one object whose momentum can be represented by this vector, and one object whose momentum can be represented by this vector? What is the total momentum of the system in this case? We can use the same graphical vector techniques that we learned in the previous DL. We just add these up tip to tail. The total momentum of the system is this long arrow. One of the key things to remember with momentum conservation is that momentum is conserved generally for the system as a whole. It may not be conserved for the individual pieces of the system. If you were to make a list of the most important concepts in physics, conservation of momentum would undoubtedly be on that list. Momentum conservation appears everywhere in physics, whether you're doing particle physics or astrophysics, or just trying to figure out how a car works. Momentum conservation is ubiquitous. Next time, we'll do some more explicit examples of momentum conservation and see how to work out the math in some of these cases.